Hello everyone, I'm Wyeth Johnson, Technical Art Director at Epic Games, and today I want to talk about the evolution of our next generation programmable VFX tool, Niagara. We first unveiled Niagara at the GDC 2018 session Programmable VFX with Unreal Engine's Niagara, which gave everyone a glimpse of where real-time VFX was headed, a fully programmable, modular, performant tool. We've now used Niagara in production on a massive game, Fortnite, high-end demos such as Troll and Chaos, virtual production, film, collaborations with our early adopters, forum users, and of course, now Unreal Engine 5. We've learned a ton along the way. Let's watch a brief recap. Before we begin, let's briefly discuss what Niagara is and why we made it. Unreal Engine's legacy particle effect editor, Cascade, has served us incredibly well throughout Unreal's long history. Over time, however, we started to run into limitations. The behaviors were fixed function and hard-coded, and we needed more flexibility, more power, and most importantly, we needed to move the output of the simulation into the hands of artists, like we did in Unreal Engine 3 with the material editor. Niagara is the answer to that need. It's a programmable, node-based editor which allows artists to control every aspect of their simulation and rendering. Underlying behaviors are written in a node graph, or for those highly technical, directly in HLSL. And then the resultant behaviors are cross-compiled on both the CPU and GPU, and can be packaged up into compartmentalized individual functions called modules, which can be snapped together like building blocks to create complex and intricate behaviors. This approach lets effects artists work without a deep technical burden by placing pre-authored behaviors into a module stack, which flows from top to bottom, while also giving unprecedented power to technical artists and programmers to create anything they can imagine and share it with their team. Niagara systems are built from multiple emitters. Each emitter can be standalone or an on-disk asset, which can be art-directed and reused to build up a library of common effects and save artists the time of rebuilding the same things over and over again. These assets also support chained inheritance, with master emitter behaviors feeding into child variants to create a variety of effects easily from a single common behavior. In Niagara, simulation and rendering are also decoupled, allowing a single point simulation to be rendered multiple times, for instance as both sprites and meshes. Artists can choose the complexity of their interactions with the tool. They can stay high level, modifying the pre-supplied inputs on existing modules with new values, or the included dynamic inputs such as random numbers, math operations, and so on. For the more technical, completely new behaviors can be created inside of node graphs, where existing particle attributes, such as position, velocity, or color, can be read in, modified, and written back out. Lastly, power users can write HLSL expressions directly into module inputs or node graphs, if desired. Niagara is an FX framework, not just a particle simulation tool, and will evolve heavily alongside future generations of hardware, software, and the needs of our users. So what are we going to talk about today? First up, I'd like to talk about some of the improvements we've made for the interface, usability of the tool. We've made a lot of enhancements to performance and scalability, forged in the crucible of shipping a massive game like Fortnite. Of course, we've added a bunch of new features and capabilities to the engine and tech. We should talk about those. And then we've got some experimental things, some things that aren't quite finished, but which are really exciting. First up, let's focus on some UI and UX improvements. So let's start with the main presentation. First off, you notice this new view into your effects. We call it the system overview. And the main thing we're solving here is we were missing that 30,000 foot view of your system and all the constituent emitters that make it up. So this view allows for comments, grouping, and kind of an expression of artistic intent during creation. These are the magical sparks, here's the flying debris, here are the fire elements all separated out. And we think this view will be home to more things in the future. We could see a world where simple data flow, like the sending and receiving of events or communication of attributes between emitters, is represented here. So users could see all their interactions between emitters in one place. If we move on to the stack, we've got a lot of visual enhancements there. Of course, visual polish, color palette changes, icons, prompts, warnings, a better utilization of white space. Colors have been unified and contrast has been increased overall just for readability. And this is an area where lots of little things help a lot. So for instance, there's just a little visual indicator if an emitter is CPU or GPU. And we've got this subtle feature we're calling highlights, which are those colored squares. They just help guide some intuition about what modules do, what their behaviors are. Orange apply forces, red deals with position, that kind of thing. Another important thing is we have full copy and paste everywhere. Copy and paste works on emitters, modules, dynamic inputs, anything. Pasting works in context and adapts to the pasted inputs correctly even across modules. So if you had a duplicate module and you wanted to take the parameterization from one, paste it into the other, it would do its best to match those up. This is also a big lifesaver for dynamic input chains, or if you've created a module variant and want to get that data copied across. The same visual improvements come to the stack, multi-selection between emitters, and same improvements to drag and drop, copy and paste, and so on. You also notice that in the stack, the parameters look different now. We made some pretty significant changes there under the hood, so let's dig into that. We've completely refactored and simplified namespaces. And we limit the user just to the most meaningful options, easy to parse colors and icons. The goals here are twofold. First is just to reduce typing, and subsequently typos. And secondly, we want to codify explicit behaviors into each of these namespaces. For example, explicit inputs and outputs for data that flows through modules, true local variables inside of module scripts that aren't accessible outside of that context. Of course, all these changes are represented in the graph view as well. You can create new attributes, change namespaces of existing attributes, add sub-namespaces if you need a little bit more granularity, and so on. Each of the namespace icons is color-coded and has really clear tooltips to help guide users to what the various namespaces mean and why you'd use them. These changes should really simplify our graph interactions and should leave a lot more clear for users. So let's talk about workflow. Niagara is now in use across a number of the different asset categories for effects in Fortnite. And Fortnite's scale is massive on so many axes, users, number of platforms, and also the size of the development team. With so many artists creating content, we've learned a ton about inheritance can be improved upon. The most valuable learning is that our initial view of inheritance was too rigid. And codifying behaviors to an inheritance chain too early is problematic, and often development mandates more flexibility than you can account for when you first plan a pipeline. This led us to a number of enhancements to inheritance. First off, emitters can now have a full inheritance chain: parents, children, grandchildren, and so on. And you can reparent emitters now. If you need to remove a behavior from an emitter kind of midstream, through the hierarchy of inheritance, we can support that. While working with inheritance, it also became clear that the flow of requiring on-disk assets for basic behaviors just wasn't desirable in all cases. Oftentimes you just want to play or generate a system outside of the context of a codified emitter behavior. So we've also leaned into defining two separate behaviors for that, and you can choose them with a new system creation wizard. So this results in your system being derived either from template behaviors, and these aren't art-directed necessarily. There's no inheritance chain with these. This is just a functional thing like burst radially or make a beam, that kind of thing. Or you can derive them from codified emitters that are art-directed and inherited. And we also support breaking inheritance and creating fully independent copies of these. And for those of you that are used to working the cascade way, i.e. with no inheritance and a completely standalone unique particle effect, we now support that. This frees up artists to play, to experiment, and to create systems without an inheritance chain or on-disk emitters if desired. Now, this idea of play leads me to the final primary area of usability we wanted to focus on. In the course of using Niagara, our general feeling is that the tool felt too rigid. To experiment with a behavior, you make an emitter, make a system, add the emitter, and the new template behaviors cover making that simpler and better. Then, however, you would make a module on disk, you add it to your stack, you experiment, you finally get to the stage where you can actually play, and then you decide you don't want it. And you're left with a series of assets on disk and these kind of half-discarded ideas. It's too rigid. So to that end, we have a new panel we're calling Scratchpad. It's a completely transient script and lives inside of your emitter or your system. It can be a module or a dynamic input. You can create the script inline or use whatever graph logic to generate behaviors you would normally, and then that script will be saved alongside that asset. If the behavior is a one-off, leave it there with a comment and move on. If you love that behavior and people on your team will too, or you'd like to reuse it, promote the Scratch behavior out to an asset on disk, and it'll be exposed to the library. Scratch behaviors can be created inline in the system overview or the stack. They can be full modules or just little custom dynamic inputs to drive a module behavior. That's a great option if your dynamic input chain is getting long and unwieldy and a little hard to read. When created, a new module is created in the Scratchpad pane. You can expose inputs, add metadata, do everything you would in the normal Niagara graph editor. And that resultant behavior is saved, embedded in the emitter or system it was added to, and it can be inherited into child emitters. And when you're happy with your behavior, either keep it embedded or promote it out to a module on disk for reuse in other emitters. We believe Scratchpad was one of the big missing pieces of the puzzle, and will turn Niagara into a far more playful, experimental, artist-friendly tool. Okay, let's move on to some of the performance and scalability improvements we've made along the way. Shipping Niagara effects in Fortnite has put a tremendous focus on performance. If you're talking about shipping across a huge number of platforms from mobile devices all the way to high-end PC in Fortnite, first question anyone asks about is performance. You got to drive a lot of things, such as culling emitters on specific platforms, scaling particle counts, managing overdraw. These things can be tedious. We wanted to make the whole process more efficient. The first way we accomplish this is by sharing, if desired, emitter calculations, such as lifetime management and scalability settings. We've got new state management modules which can inherit the lifecycle calculations of the owning system, looping, delays, am I allowed to spawn particles, resulting in both a performance improvement and a workflow benefit for artists. You can now manage the lifetime and lifecycle of 10 emitters in a system all in one place, and see a performance benefit along the way. Emitters can manage their own scalability settings, but what about managing scalability at a higher level? If you allow the system to manage scalability at the system level, as opposed to per emitter, we've introduced an easy way to share those settings with something we're calling effect types. Effect types are a new asset type, assigned per particle system inside of the system properties. Their purpose is to codify a common set of scalability settings into an on-disk asset. This allows for the quick application of common settings to whole categories of effects, say weapon impacts or ambient VFX. And of course, you can always override these settings per instance if you need to do something custom. Effect types have two parts. The first is a culling feature with multiple axes. This drives a low-level, under-the-hood C++ scalability manager, which reduces systems to zero or near zero cost when culled. It supports distance culling, a max instance count, and visibility or view frustum culling. And one area we'd like to address soon is a performance or budget-based culling as well. Secondarily, there are explicit overrides for emitters themselves on each platform, and each scalability level, and an opt-in or opt-out override listed there. We hope effect types allow a larger project to make some clear, simple choices up front about scalability settings of their particle systems, and then reuse those preset choices across large swaths of their VFX library. Now let's talk a little bit about how we've improved the cost of the actual simulation. We've pushed most of the thread-safe work into the concurrent Niagara tick. And this concurrent tick is allowed to run asynchronously with all tick groups. And this gives us the best opportunity to fit into whatever holes we can on the CPU cores. You can use tick behavior to control how Niagara ticks, which by default is safety first and will follow prerequisites from the owner and all data interfaces. And we've made a variety of optimizations to that concurrent tick as well, which has resulted in an approximate 30% reduction in instruction costs and cache misses in our test assets. I've also made significant improvements to the performance of the mesh renderer on the render thread, and have also significantly reduced the cost of sorting. The vector VM performance has been improved. We now perform a bytecode optimization pass, reduces instructions, and allows memory read-write batching and vectorization on the target platform. In most cases, Niagara now meets or exceeds Cascade performance on the game thread, and beats it on the render thread. Those remaining cases where it doesn't will be areas of heavy focus for us in future releases, particularly in areas of high emitter counts in a given system, or emitters with very, very low particle counts, where you pay a lot of overhead for the emitter. And from a GPU simulation perspective, we know there's lots of low-hanging fruit from both memory and simulation cost perspective. Now on to the really fun stuff. There's a ton here, so let's start at an obvious place: data. One of the most powerful aspects of a given simulation tool is what kind of data it has access to. The flow of data from external sources or from other parts of the engine is where these types of simulations really start to shine. First up is a data interface which allows access to the properties of the current player camera. On the CPU side, we expose a limited but useful set of camera attributes. On the GPU side, we pretty much expose everything from the view uniform buffer that we think would be useful. Note that this is an early feature which still needs some work to be split screen or VR friendly, but it's incredibly powerful and something we've been clamoring for. On the GPU, we also provide a data interface to calculate occlusion. You can query a point in space and compare that point to the depth buffer by taking a number of samples around it. This can be calculated per particle, which allows for some interesting control. Combining these two powerful data interfaces allow for complex camera-based effects, such as viewer-aware simulations, VFX attached automatically to the camera, or even lens flares. Here's a fully procedural lens flare built using these new features, which was used in our Unreal Engine 5 reveal demo. Next up are two separate data interfaces, which allow access to audio waveform data. Oscilloscope provides inexpensive direct access to the audio waveform, while audio spectrum is more complex. It uses something called the constant Q transform, which is almost like a fast Fourier transform, but for audio. This separates the audio into buckets logarithmically, akin to musical semitones, and is more intuitive for listeners and viewers as the audio response matches note progression. Here's a fun little audio visualization showing a Niagara effect being driven by these audio waveforms. One other fun aspect of the audio effect you just saw was that it used Raytracing. Unreal Engine now supports Raytracing not just sprites, but mesh particles as well. Another exciting enhancement comes from our good friends at SideFX. They've created version 2 of their popular Houdini Niagara data interface, and it's excellent. The workflow is greatly simplified, just point it at a point cache, and it just works. It uses a new binary JSON format for faster import and support larger, more complex Houdini caches. The plugin now automatically handles animated caches as well, including managing particle birth, lifetime, and so on. The plugin also now works on GPU emitters, which has been very in demand. Here's a quick video of the Houdini test scene you see here, imported quickly directly into Niagara. This is a complex simulation with physics, cloth, and procedural animation, generated in Houdini and played back directly. It's exciting because that simulation still stays live and can be affected by our existing forces, creating a hybrid of pre-computed and real-time interactive simulation. Another exciting enhancement comes in the form of a data interface we're calling Attribute Reader. It allows particles to directly communicate with other particles, either in the same emitter or different emitters in the same system, and ask them for attributes, such as position or color. This allows for extremely complex behaviors such as chains or flocking, or thousands of other complex interactions. This is also addressable via custom HLSL, so you can easily write complex behaviors that require intra-particle communication. Another complementary feature alongside the Attribute Reader is our Particle Neighbor Grid 3D. This is a spatial hash which looks into neighboring cells and gathers information about your nearest neighbors. This can be used for an infinite number of things, but is common in fluid simulation, flocking, or when solving performant intraparticle collisions by only comparing particles with the nearest relevant neighbors. These last two features, the Attribute Reader and the Neighbor Grid, were combined with a swath of other techniques such as distance field sampling, custom vertex shader-based animation states, and level-aware forces to create some absolutely stunning simulations of bats and bugs 100% in Niagara in our Unreal Engine 5 demo reveal. Let's take a look.
Nice bugs. Don't mind me.
This last section is all about where we think real-time visual effects is headed moving forward. All the features here are listed as experimental, meaning they aren't necessarily production ready. However, we see these features as crucial to our vision for Niagara moving forward, and the results speak for themselves. Let's dive in. With the idea of direct reads and spatial queries exposing much more complex simulations on individual points, it naturally leads to the question of a simulation potentially being more than simply points. To that end, we've introduced a completely new type of simulation data beyond particles, Grid 2D. You can imagine each grid cell is a particle, and can be read from or written to as an array. We have transforms to move in and out of grid space, and particles can write data into grids or read from grid attributes. These features enable complex grid-based simulations and solvers. Smoke simulations, shallow water, particle in cell or flip fluids, iterative behaviors normally relegated to the land of theoretical exercise now integrate seamlessly with production particle-based effects. And the results of these grid simulations can be written out to render targets and rendered directly in standard Unreal materials or simply used as a data structure to hold information about your simulation. Users can have multiple grids and multiple attributes per grid. You can read and write to grids with nodes or custom HLSL. This is a powerful, persistent data structure that will unlock Niagara in amazing ways as we move forward. The feature which ties all of these other innovations together and truly unlocks their power is something we're calling simulation stages. This is a GPU-only feature, and the core concept is the idea of performing multiple iterations in a single update tick, directly in the stack UI. Each simulation stage becomes another script that runs, like spawn or update. You can have as many stages as you like, and what's incredibly powerful is you can iterate not only over particles, but also data interfaces. For example, iterating over every grid cell in your Grid 2D to create complex feedback-based solvers directly in Niagara. Now, the implementation of these types of complex algorithms is something you can do directly in the interface. And because they share data with the rest of the simulation behaviors and can talk freely between particles and grids, these types of algorithms are no longer relegated to the land of creative coding exercise. These complex features will be able to integrate with our existing particle behaviors seamlessly and work side by side. Imagine having a preset suite of module behaviors, for example, fluid simulation, or a mold growth algorithm, or a PBD solver. And those behaviors are applied alongside the existing forces in your simulation, such as curl noise or gravity, and solved together in the same solver to affect particle simulations and behaviors in new and interesting ways. We've used these experimental features in a series of short vignettes, rendered in real time, to show you the power of what the attribute reader, grid 2D, and simulation stages can do. And we're just scratching the surface. Let's take a look. We hope you've enjoyed this look into Niagara and what the future holds. Everything you've seen here, including early access to these experimental features, is available in Unreal Engine 4.25. Have fun.